Hey everyone, Mr. Armitage here, and in this video for Algebra 2, we are looking at the multiplicities of roots, so seeing kind of what they look like. So here is a polynomial, okay, a 10th degree polynomial, leading coefficient of 1, which is positive, so we see end behavior going up, tie it all together. Okay, so x to the 10th plus 8x to the 9th plus 18x to the 8th minus 8x to the 7th minus 67x to the 6th minus 24x to the 5th plus 88x to the 4th plus 32x to the 3rd minus 48x squared. Notice that there is no, at present, term with x, just x, or a constant term. Okay? If you wanted to try to factor this on your own, really test out those factoring skills, okay, I'll give you 2 hints. First hint, there is a greatest common factor that you can take out of everything here, which would reduce it to an 8th degree polynomial, degree of 8. Okay, and that would actually give you one of the roots that we can see here. After that, so after you take out that greatest common factor, then you will need to use the rational root theorem to actually solve this, or to factor it. That was the second hint. If you want a third hint, okay, obviously you can see by the graph that I have here, there are no roots bigger than plus or minus 4. Okay. So if you want to, you can pause and then come back, and I will show the answers. Okay, so for those of us who stayed on, or if you're just returning, if we factor this, okay, this is what we would get. Okay, f of x equals x squared, which was the greatest common factor, okay, times x plus 3 times x plus 2 to the 4th power times x minus 1 to the 3rd power. Okay, and this is here, okay, this graph here is the graph of that polynomial, okay, both of them, the standard form and the factored form. So we can easily get the roots from this. Right, so we have x equals 0 from the x squared, okay, which is right there. We have the x minus 3, or sorry, the x equals negative 3 right there. Here we have x equals negative 2 right there. And we have x equals positive 1 right there. And now we should see from these roots that they all look slightly different. Okay? Even this one looks a little bit different than this one, but not too much. And so why is that? That's because these factors appear multiple times when we actually factor everything out. Let's go ahead and, well, we can see the multiplicities. Okay. Here, x squared, okay, if that is x equals 0, that means x equals 0 appears twice. So that's a multiplicity of 2. X plus 3, there's no exponent shown on there, which means there's only a 1. So that's a multiplicity of 1. X plus 2, so x equals negative 2, that has an exponent of 4. So that means that that factor and that root, well, the factor appears 4 times. The root has a multiplicity of 4. X minus 1 as a factor appeared 3 times because its exponent is 3. And the root then x equals positive 1 has a multiplicity of 3. And notice the common patterns here. Okay. If we look at these roots, okay, specifically the multiplicity of 2 and the multiplicity of 4, these look kind of the same, or at least similar. Right? This one here, the -2 root, is just a little bit flatter than the 0 root. Okay? And that's what happens with even multiplicities. Okay? They just touch that root and bounce back. But the higher the power, the flatter that sort of touch is. For an odd multiplicity that is 3 or greater, okay, we have this kind of swerve like this. It goes through the root just like a multiplicity of 1 root does. Okay? But rather than just going straight through like a line, it kind of does almost this cubic-like swerve through it, which is exactly it. And this shares the same features as the even multiplicities, where if you have a higher multiplicity, like 5, 7, 9, it's going to get sharper. Okay? It's going, or flatter, if you will. And we can actually see what that looks like. But right now, we have these roots. We know their multiplicities. And so we can see how they touch or go through their roots. So here, let's go ahead and look at sort of what those higher powers of multiplicities look like. Okay, so here I have Desmos open, and you can see that the original polynomial that we used is in here, so that's fine. I'm going to go ahead and hide that. Let's look at the even multiplicities. Okay, so they kind of look like a parabola, and specifically, okay, this would be x squared, which has a root at x equals 0 with a multiplicity of 2. Now, if we increase that to 4, okay, that's flatter. That's what we saw in the original polynomial. It's x to the 4th power. Now, the 6th, the 8th, the 10th. Notice it's getting flatter and flatter, right? Or sharper. Okay, it comes down at a steeper angle, or would go up if it was on the other side, and it's flatter next to the axis. So specifically, it kind of looks like this as we change it. But it's always that kind of bowl-shaped. It's just touching the root. So let's look at the odd multiplicities, the ones that are greater or 3 or greater than 1. 1 is technically an odd number, but that's its own special multiplicity. So 3 or greater for an odd multiplicity. Okay, this is x to the 3rd. It has a root of 0 that it passes through. X to the 3rd equals 0. So x equals 0 3 times. And this is just a basic cubic function. If we do x to the 5th, okay, a little steeper on the edges, a little flatter in the middle. 7th, it's the same thing, just going like this. Okay? But it always passes through the root. So in our class, we don't really deal with multiplicities greater than 3. Right? We either have multiplicity of 1, so just the simple roots, multiplicity of 2, or a multiplicity of 3, sometimes. Okay. And that's because at that point, the polynomials can get really big, which we saw here, where our polynomial had 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, okay, and a total of, well, 1, 2, 3, 4 unique roots. But with those 4 unique roots or factors, okay, we had a multiplicity, so x equals 0 happened twice, so there's 2, 3, and then up to 7 for those 4, and then 10. So we have 10 factors, or 10 roots total, when we include multiplicity. Look at what the degree is. And that's all I'll say about that.